Structural engineers are most commonly involved in non-building structures, as well as building structures, but they can also be involved in the design of machinery, medical equipment, vehicles, or any item where structural integrity affects the item's function or safety. Structural engineers must ensure their designs satisfy given design criteria, predicated on safety or serviceability and performance. Structural engineering theory is based upon applied physical laws and empirical knowledge of the structural performance of different materials and geometries. Structural engineering design utilizes a number of simple structural elements to build complex structural systems. Structural engineers are responsible for making creative and efficient use of funds, structural elements and materials to achieve these goals. Structural engineer. Structural engineers are responsible for engineering design and analysis. Entry-level structural engineers may design the individual structural elements of a structure, for example the beams, columns, and floors of a building. More experienced engineers may be responsible for the structural design and integrity of an entire system, such as a building. Structural engineers often specialize in particular fields, such as bridge engineering, building engineering, pipeline engineering, industrial structures, or special mechanical structures such as vehicles, ships or aircraft. Structural engineering has existed since humans first started to construct their own structures. It became a more defined and formalized profession with the emergence of the architecture profession as distinct from the engineering profession, during the Industrial Revolution in the late 19th century. Until then, the architect and the structural engineer were usually one and the same, the master builder. Only with the development of specialized knowledge of structural theories that emerged during the 19th and early 20th centuries did the professional structural engineer come into existence. The role of a structural engineer today involves a significant understanding of both static and dynamic loading, and the structures that are available to resist them. The complexity of modern structures often requires a great deal of creativity from the engineer in order to ensure the structures support and resist the loads they are subjected to. A structural engineer will typically have a 4 or 5 year undergraduate degree, followed by a minimum of 3 years of professional practice before being considered fully qualified. Structural engineers are licensed or accredited by different learned societies and regulatory bodies around the world, depending on the degree course they have studied or the jurisdiction they are seeking licensure in. They may be accredited as just structural engineers, or as civil engineers, or as both civil and structural engineers. Another international organization is IABSE. The aim of that association is to exchange knowledge and to advance the practice of structural engineering worldwide in the service of the profession and society. History of structural engineering. Structural engineering dates back to 2700 BCE, when the step pyramid for Pharaoh Djoser was built by Imhotep, the first engineer in history known by name. Pyramids were the most common major structures built by ancient civilizations because the structural form of a pyramid is inherently stable and can be almost infinitely scaled. However, it's important to note that the structural stability of the pyramid is not primarily a result of its shape. The integrity of the pyramid is intact as long as each of the stones is able to support the weight of the stone above it. The limestone blocks were taken from a quarry near the build site. Since the compressive strength of limestone is anywhere from 30 to 250 megapascals, the blocks will not fail under compression. Therefore, the structural strength of the pyramid stems from the material properties of the stones from which it was built rather than the pyramid's geometry. Throughout ancient and medieval history, most architectural design and construction was carried out by artisans, such as stonemasons and carpenters, rising to the role of master builder. no theory of structures existed, and understanding of how structures stood up was extremely limited, and based almost entirely on empirical evidence of what had worked before. Knowledge was retained by guilds and seldom supplanted by advances. Structures were repetitive, and increases in scale were incremental. No record exists of the first calculations of the strength of structural members or the behavior of structural material, but the profession of structural engineer only really took shape with the Industrial Revolution and the reinvention of concrete. The physical sciences underlying structural engineering began to be understood in the Renaissance and have since developed into computer-based applications pioneered in the 1970s. Timeline: 1452 to 1519. Leonardo da Vinci made many contributions. 1638. Galileo Galilei published the book Two New Sciences, in which he examined the failure of simple structures. 1660. Hooke's Law by Robert Hooke. 1687. Isaac Newton published Philosophiae Naturalis Principia Mathematica, which contains the Newton's laws of motion. 1750. Euler-Bernoulli beam equation. 1700 to 1782. Daniel Bernoulli introduced the principle of virtual work. 1707 to 1783. Leonhard Euler developed the theory of buckling of columns. 1826. Claude Louis Navier published a treatise on the elastic behaviors of structures. 1873. Carlo Alberto Castigliano presented his dissertation, Intorno ai sistemi elastici, which contains his theorem for computing displacement as partial derivative of the strain energy. This theorem includes the method of least work as a special case. 1874. Otto Moore formalized the idea of a statically indeterminate structure. 1922. Timoshenko corrects the Euler-Bernoulli beam equation. 1936. Hardy-Cross publication of the moment distribution method, an important innovation in the design of continuous frames. 1941. Alexander Renikoff solved the discretization of plane elasticity problems using a lattice framework. 1942. R. Courant divided a domain into finite subregions. 1956. J. Turner, W. Clough, C. Martin, and L. J. Top's paper on the stiffness and deflection of complex structures introduces the name of finite element method, and is widely recognized as the first comprehensive treatment of the method as it is known today. Structural failure. The history of structural engineering contains many collapses and failures. Sometimes this is due to obvious negligence, as in the case of the Pétionville School collapse, in which Rev. Fortin Augustin constructed the building all by himself, saying he didn't need an engineer as he had good knowledge of construction, following a partial collapse of the three-story schoolhouse that sent neighbors fleeing. The final collapse killed 94 people, mostly children. In other cases, structural failures require careful study, and the results of these inquiries have resulted in improved practices and greater understanding of the science of structural engineering. Some such studies are the result of forensic engineering investigations where the original engineer seems to have done everything in accordance with the state of the profession and acceptable practice, yet a failure still eventuated. A famous case of structural knowledge and practice being advanced in this manner can be found in a series of failures involving box girders which collapsed in Australia during the 1970s. Specializations. Building structures. Structural building engineering includes all structural engineering related to the design of buildings. It is a branch of structural engineering closely affiliated with architecture. Structural building engineering is primarily driven by the creative manipulation of materials and forms and the underlying mathematical and scientific ideas to achieve an end which fulfills its functional requirements and is structurally safe when subjected to all the loads it could reasonably be expected to experience. This is subtly different from architectural design, which is driven by the creative manipulation of materials and forms, mass, space, volume, texture and light to achieve an end which is aesthetic, functional and often artistic. The architect is usually the lead designer on buildings, with a structural engineer employed as a sub-consultant. The degree to which each discipline actually leads the design depends heavily on the type of structure. Many structures are structurally simple and led by architecture, such as multi-story office buildings and housing, while other structures, such as tensile structures, shells and grid shells, are heavily dependent on the form for their strength, and the engineer may have a more significant influence on the form, and, hence much of the aesthetic, than the architect. The structural design for a building must ensure that the building is able to stand up safely, able to function without excessive deflections or movements which may cause fatigue of structural elements, cracking or failure of fixtures, fittings or partitions, or discomfort for occupants. It must account for movements and forces due to temperature, creep, cracking and imposed loads. It must also ensure that the design is practically buildable within acceptable manufacturing tolerances of the materials. It must allow the architecture to work, and the building services to fit within the building and function. The structural design of a modern building can be extremely complex, and often requires a large team to complete. Structural engineering specialties for buildings include earthquake engineering, facade engineering, fire engineering, roof engineering, tower engineering, wind engineering, earthquake engineering structures. Earthquake engineering structures are those engineered to withstand earthquakes. The main objectives of earthquake engineering are to understand the interaction of structures with the shaking ground, foresee the consequences of possible earthquakes, and design and construct the structures to perform during an earthquake. Earthquake-proof structures are not necessarily extremely strong like the El Castillo Pyramid at Chichen Itza shown above. In fact, many structures considered strong may in fact be stiff, which can result in poor seismic performance. One important tool of earthquake engineering is base isolation, which allows the base of a structure to move freely with the ground. Civil engineering structures. Civil structural engineering includes all structural engineering related to the built environment. It includes the structural engineer is the lead designer on these structures, and often the sole designer. In the design of structures such as these, structural safety is of paramount importance. Civil engineering structures are often subjected to very extreme forces, such as large variations in temperature, dynamic loads such as waves or traffic, or high pressures from water or compressed gases. They are also often constructed in corrosive environments, such as at sea, in industrial facilities or below ground. Mechanical structures. Principles of structural engineering are applied to a variety of mechanical structures. The design of static structures assumes they always have the same geometry, but the design of movable or moving structures must account for fatigue, variation in the method in which load is resisted and significant deflections of structures. The forces which parts of the machine are subjected to can vary significantly, and can do so at a great rate. The forces which a boat or aircraft are subjected to vary enormously and will do so thousands of times over the structure's lifetime. The structural design must ensure that such structures are able to endure such loading for their entire design life without failing. These works can require mechanical structural engineering, boilers and pressure vessels, coachworks and carriages, cranes, elevators, escalators, marine vessels and hulls. Aerospace structures. Aerospace structure types include launch vehicles, missiles, hypersonic vehicles, military aircraft and commercial aircraft. Aerospace structures typically consist of thin plates with stiffeners for the external surfaces, bulkheads and frames to support the shape, and fasteners such as welds, rivets, screws and bolts to hold the components together. Nanoscale structures. A nanostructure is an object of intermediate size between molecular and microscopic structures. In describing nanostructures, it is necessary to differentiate between the number of dimensions on the nanoscale. Nanotextured surfaces have one dimension on the nanoscale, i.e., only the thickness of the surface of an object is between 0.1 and 100 nanometers. Nanotubes, disambiguation needed, have two dimensions on the nanoscale, i.e., the diameter of the tube is between 0.1 and 100 nanometers, its length could be much greater. Finally, spherical nanoparticles have three dimensions on the nanoscale, i.e., the particle is between 0.1 and 100 nanometers in each spatial dimension. The terms nanoparticles and ultrafine particles often are used synonymously, although UFP can reach into the micrometer range. The term nanostructure is often used when referring to magnetic technology. Structural engineering for medical science. Medical equipment is designed to aid in the diagnosis, monitoring or treatment of medical conditions. There are several basic types. Diagnostic equipment includes medical imaging machines, used to aid in diagnosis. Equipment includes infusion pumps, medical lasers and LASIK surgical machines. Medical monitors allow medical staff to measure a patient's medical state. Monitors may measure patient vital signs and other parameters including ECG, EEG, blood pressure, and dissolved gases in the blood. Diagnostic medical equipment may also be used in the home for certain purposes, e.g., for the control of diabetes mellitus. A biomedical equipment technician is a vital component of the healthcare delivery system, employed primarily by hospitals. BMETs are the people responsible for maintaining a facility's medical equipment.